Okay, so if you recall in the last lecture, which was the first lecture of this course, we had introduced the concept of semiconductor and why semiconductors are very essential in today's world, and we also introduced the concept of bands, energy bands, how bands are formed. We also introduced the concepts of reciprocal space and EK diagram, but we shall revise that once again today. So the main take home lessons we learned last time was that number one, semiconductors have a unique property, which is that you can tune their conductivity between metals and insulators. Sort of, you can do many order of magnitude change in their resistance by adding impurities or by doing some other techniques, which is not possible in metals or in insulators, right. So, and another thing number 2 is that they have a gap between the highest occupied band and the lowest unoccupied band, and that gap is called energy band gap, which is not too high unlike insulator, and in metal there is no gap, right. So, semiconductors have these two very important properties, and since semiconductor is a solid, it is a crystal, right. So, many of the properties will depend on how the crystal is, and it is as much as material science as devices, and we shall learn subsequently in the course that we have to study both the materials physics as well as the device aspect together to understand how the devices work, how technologies are made. Okay. So, we shall come back to the whiteboard again. Last time I had told you that energy E and momentum are related by this relation, if you recall, h bar square k square by 2 m. What was k here? K actually is a reciprocal space vector, but you can visualize it as momentum because h bar times k gives you the momentum, right. So, you can think of k as momentum, it is a momentum direction, okay. And energy depends in a quadratic relation to momentum. This actually comes from high school physics only, p square by twice m is equal to kinetic energy, if you recall, right. That actually what it comes from. This all was valid for a free electron in a space, right, an electron free in space where there is no no boundary, no crystals, nothing. In that case energy and k has a parabolic relation, right, like that, and we call that this is a free parabola, of course, and energy and k has this parabolic relation, and that is very good, we learned that. Now, I told you that when an electron moves in a crystal, it sees this periodic atoms, right. There is a periodic arrangement of atoms in 3D. Here I am drawing it only in 2D. Okay, here I am drawing only in 2D. Sorry, I will come back to the page again. So, there is this atoms which are arranged in 3D, and an electron has to go through the crystal when an electron moves in a semiconductor. Why are we studying this? We are studying this because we want to eventually understand how current flows in semiconductor, right. We want to understand eventually how current flows in semiconductor. And why do you want to understand why current flows in semiconductor? Because only then we can understand different devices like LEDs, MOSFETs and so on, right. So, how current flows in semiconductor, we need to understand the transport of electricity, and current is carried by electrons and another type of particle called holes, I will come to that. So, we need to understand how electrons actually move in a crystal. Now, a semiconductor, to be actually a semiconductor and have a band gap, it should have this periodic arrangement of atoms which are highly periodic in nature. Okay. In any direction you look, the crystal structure will look the same, it is called crystalline material, unlike a piece of glass or wood or like some oxide where basically you have an amorphous sort of a structure where the crystal, this atoms are not arranged in a definite lattice. Okay. So, we are talking about semiconductor crystal. So, we can assume that these are periodic, actually these are periodic, in a periodically they are arranged, and each of these atoms actually introduces a potential, right. Each of these atoms introduces a potential, and it is called a periodic potential. Okay. It is called a periodic potential. So, essentially an electron has to move, okay, in a periodic potential, it has to move in a periodic potential, and that periodic potential is set up by the atoms, right. All the atoms that are there in the crystal set up this periodic potential, and electrons have to move in the periodic crystal. So, when electrons move in a periodic potential in actually a semiconductor crystal like say silicon, then this EK diagram that we had drawn, no, this EK diagram, if you remember, this is E, this is K, this EK diagram that we have drawn becomes a little bit distorted. Okay. It becomes a little bit distorted when electrons move in a actually a periodic crystal, okay, periodic potential. Okay. It is not in free space. Only in free space electron has this EK relation where energy is proportional to k square. Actually, this diagrams means that as you increase the momentum of a electron, the energy will increase parabolically with respect to that momentum. That's basically what it means, right? So, and remember that there was the h square k square by 2 m there, that m was the mass of electron, we say, right? In free space, this is the mass of free electron, and you know that mass of free electron is m naught actually, which is given by 9.1 into 10 to the minus 31 kg, right? But this mass actually is the mass of electron when it moves in free space. Now, I told you that when electrons will move in a periodic potential in a semiconductor crystal, then first thing that will happen is that this EK diagram actually becomes distorted, and that is mathematically can be proved. We shall not derive that expression here, but you can mathematically prove that this EK diagram becomes distorted. And so, when the electron moves in the periodic crystal, if you can try to visualize it physically, okay, not mathematically so much, when an electron moves in this periodic potential, then it sees that periodic potential along with variation, no. So, the electron experiences a different sort of acceleration. It experiences, you can say that it has a different mass inside the periodic potential. So, I told you that these different atoms, if I take a one dimensional string of atoms only, right, these atoms will introduce, you know, they have a own potential. So, I told you that they actually introduce a potential wells like that, right, and this potential profile can be actually modeled by a very simplistic argument, you know, like people do that kind of a, this is suppose A, okay, this is again A, this is like the lattice constant. Remember, A is the spacing between adjacent atom, it is called lattice constant, okay, spacing between adjacent atoms, okay, adjacent atoms, it is called lattice constant, okay, it is also called lattice constant, okay. So, you have this infinitely deep potential L, this is infinite, you can assume this is infinite, and these are delta functions, you know, where essentially your electron, the nuclei of the atoms lie, they are like delta functions, they are delta spikes, and you have this periodic potential. So, you solve the equations, you know, you solve the equations basically of an electron as it moves inside a periodic potential. That is what you do. You have to solve some quantum mechanical equations, we are not touching in those in this course, but if you solve that, then you will find out that actually this EK diagram, okay, this EK diagram becomes distorted. How does it become distorted, you know? I will draw it a better picture. So, what did I tell you? I told you that when the electron actually, you can model the periodic potential of atoms as this infinite quantum wells, a delta function of this ion cores, they are all A here, and you have to solve the motion of electron inside this periodic quantum well or periodic potential well, okay. The motion of electron when an electron moves, because electron is a subatomic particle, no, it basically has both electron the particle and wave like nature. So, to understand the motion of electron, you have to solve an equation called Schrodinger's equation, okay. You have to solve an equation called Schrodinger's equation. It was actually derived and proposed by Erwin Schrodinger. He was a physicist in the 1920s. He got the Nobel Prize at a very young age for doing this pioneering work. So, Schrodinger's equation is actually an equation that basically equates the energy of electrons in a way, and there is something called a wave function psi. We will not go into the details. Psi is actually called a wave function, and it basically, just like, you know, if you throw a stone in a pond of water, you have these waves, right. So, you can model the electron also as a wave, you know, and that there is a wave function associated with it, okay. You know that it is impossible to exactly find out the location of electron and determine its velocity or momentum simultaneously, right, that is Heisenberg's uncertainty principle. So, what you can do is always you can give a probability of finding the electron, okay. You can always give a probability of finding the electron. You can never guarantee and say that this is where the electron is, you can only give a probability, and apparently psi of x, okay, its modulus whole square gives you the probability of finding electron, okay. So, this is a wave function of the electron, and you have this Schrodinger's equation actually depends on this wave function of the electron. You solve that, you know, for a free space, then you get that EK diagram also, you know, and if you solve it for this periodic potential where there is this periodicity of this potential, then you can get the actual Schrodinger's equation solution for an electron inside a semiconductor crystal, which is periodic in nature. And as I told you, it has to be periodic only, then the concepts of energy band gap actually can be used, right. So, that is why that is another reason why it has to be periodic, by the way. So, if you do that, then you will see that the EK diagram actually becomes distorted. So, what was the EK diagram before? Let me draw it again. So, this is E, okay. What I keep selling as EK diagram actually is an energy momentum diagram, in a way you can think of it. So, initially the EK diagram was something like this. My drawing is not very good, but it's a parabola, a very nice parabola. But this is in free space. When in periodic crystal, the EK diagram becomes distorted in the sense that it will have a shape here like almost like that, but after some time it will become like that. Okay, it will open up, and there is a discontinuity here. There is a discontinuity. So again, it will start from here. I'm not doing it very well. Sorry, I made it mistake. Anyways, so it will again start from something like that. It will again start from something like that. So there are these gaps that appear here, right? There are these gaps that appear here. My drawing is not very good, but of course they are symmetric. So you have these gaps here, and if you remember, in free space it is a smooth parabola like this. Okay, it's a smooth parabola like this, no discontinuity. But in a periodic potential, there is this discontinuity. There is discontinuity because if you consider this first band here, first curve here, it has a band here. There's a gap. There's a gap here. You see, there's a gap here. You see, and this discontinuities, these distortions, the deviation from the smooth parabola happens. This actually is like that. Actually, it here and here. This is the same point. Actually, by the way, okay, this is the same point. This is the same point. This all happen at spacings of pi by a, 2 pi by a, whatever, then again there will be distortion at 3 pi by a, here similarly minus pi by a, minus 2 pi by a, and so on. Okay, you have these distortions actually. A is the lattice constant of the crystal, which means the spacing between adjacent atoms. So you know that. So pi by a is of course the unit is centimeter inverse, by the way. So every pi by a, 2 pi by a, 3 pi by a, n pi by a, you have these distortions that come out. Okay, and this is the actual shape of the EK diagram for an electron that moves in a periodic potential. And you can see that this first, the lowest level or even the higher levels, they are not exactly parabola, they are parabola towards k equal to 0 point. This is k equal to 0, but as you go away from the k equal to 0 point, your deviation occurs substantially and it is no longer parabola, it becomes little curved other way around, right. So the curvature changes. Okay, the curvature changes, and to understand now why are we studying all this, you have to always ask this question as to why are we studying the EK diagram of electrons that are moving in a periodic potential. Because electrons move in actual semiconductor crystal when they carry current, and this EK diagram is very much there. We cannot see it physically, but it's actually there, and this relation, the energy and momentum relation of electrons is most fundamental in understanding the transport properties, in understanding the band diagram, in designing devices, so many things. Okay, it is very fundamental to understanding the electron transport in a semiconductor crystal. That's why we are understanding. There's a lot of physics that has gone into it, lot of Nobel prizes have been awarded on this, but we shall actually talk about it very simplistically, not going into much of mathematical details. That's what I am trying to do here. It so happens that most of the semiconductor devices that we learn or we will study in this course, whether it is BJT, MOSFET, LED, photodetector, doesn't matter, we can always consider everything to be happening, or we can basically understand everything by understanding this first block here. We do not have to go to this, we do not have to go to this. Okay, these are higher order, you can say zones. You can only consider between minus pi by a to pi plus pi by a. Okay, only this particular zone, of course this is here. So let me draw it again. Okay, all the semiconductor transport, all the devices, all the concepts of physics and transport, everything can be understood only in the first gap here. So this is k, okay, and I told you this is pi by a and this is say minus pi by a, right. So it will be something like that, right. I told you it's a little deviated from parabola. Of course there are higher order bands that start here, but we will not need that so much. Okay, this zone that I am talking about within pi plus pi by a minus pi by a is called the first Brillouin zone. Okay, Brillouin zone. There is a scientist actually named Brillouin, actually he made this thing. So first Brillouin zone. So this is the first zone where most of the electrons actually will be there, and most of our device transport physics will also happen here. Okay, this is the EK diagram of a real electrons that are moving inside semiconductor crystal. That's number one thing. Number two is that this is not exactly a parabola. This is a slight non-linearity as you go away from 0 to k by a, pi by a. When I say you go from 0 to pi by a, it's not physical distance you are going, by the way. 0 to pi by a, your k is changing, it means your momentum is increasing. So, at k equal to 0 your momentum is 0, but at here the momentum has become some finite number. So, when you increase the momentum essentially you have this non parabolic sort of relation eventually, okay. And this essentially, but most of the things this you can see that this is energy on the y axis. So, this point is at higher energy than this point. Most of the electrons will be close to here only, okay, very low energy. We talk about low energy, and so at close to 0 it is perfectly parabola, okay. It's, you can say it's a very nice parabola at close to k equal to 0, and mostly we will talk about k equal to near 0 only, okay. So, this is the energy, and we can say this is like a, you can say this is like a band, of course, where electrons are populating. Electrons will populate as you have more electrons, it will start populating more, but we will mostly have, we will concern only about near k equal to 0, okay. So, this is actually a equal to h square k square by twice m still holds true for this particular distorted parabola of a real semiconductor crystal when electrons move, except that this m is no longer the free electron mass that we are talking about in space. This m has a special meaning now. This m actually we call it m star, okay, and it is called the effective mass, okay. It is called the effective mass of electron. So, effective mass of electron means what is the mass of electron as it experiences when it moves inside a periodic potential in a semiconductor crystal, okay, and it is mostly different from the free electron mass, okay. So, another way of looking at it is that if I write E equal to h bar square k square by twice m, and then I take a derivative of E with respect to k, okay, the slope of Ek diagram, then I get what, h square by into k by m star, right, that is the derivative. Now, I take another derivative d square E by d k square. What do you get? You get h square by m star. So, what I can write is, if I can write it again here, right, I can write m star as equal to, right, h bar square divided by d square E by d k square. So, what does it mean actually? If I take a E and k diagram, and I told you this looks like this, for example, this is pi by a, this is minus pi by a, of course, this line does not exist, this is my this thing, okay. So, dE by dk is basically the slope, but d square E by dk square, it is called actually what, do you know, it is called curvature. It is called curvature of a plot or diagram, okay. So, essentially h square, okay, essentially h square, which is constant, divided by the curvature of the Ek diagram, that ratio gives you the effective mass. That actually tells you the mass of electron as it moves inside a crystal. Now, h square is constant, so forget about it. So, basically the mass of an electron as it moves inside a crystal is actually inversely proportional to the curvature of the Ek diagram. So, the energy and momentum has a relation, this energy and momentum has a relation. The curvature, the inverse of the curvature, okay, the inverse of the curvature is proportional to the mass. It may not make physical sense to you right now, but we will try to see what physically it means, okay. One thing is that this Ek diagram comes from actually a quantum mechanical solution. I told you Schrodinger's equation and everything has to be solved to get this exact thing. So, the number one thing that is there is that because you define the effective mass as h square by d square E by dk square, and I told you that this comes from proper quantum mechanics, this Ek diagram, right, and the Schrodinger solution, right, Schrodinger solution it comes, right, that Ek diagram. So, essentially when you define effective mass like that, this effective mass concept takes into account what does it take into account? It takes into account the band structure information of the material, the band structure information on the material, on the particular material you are talking about, okay. This Ek diagram that I told you, that Ek diagram that I have been telling you here, this Ek diagram actually is sort of a, it's called a band structure, okay. This Ek diagram itself is called band structure. How energy of electron changes with momentum, that is actually called band structure. It comes from quantum mechanics. I told you it is very heavy physics, but the entire band structure information is actually condensed and crisply put into this d square E by dk square expression. So, when you have this effective mass defined this way, you do not have to solve any quantum mechanical equation separately. This particular expression of the derivative, second derivative of the Ek diagram takes into account entire physics and quantum mechanics that is inside the band structure. So, what does it mean? It means that all the classical physics equation, all the classical physics equations, for example, F equal to ma, that is the Newton's second law of motion, right. For example, acceleration times mass is force. All this classical physics equation can be applied now, can be applied to electron. See, electron is a subatomic particle, the quantum mechanical properties have to be included when we study transport of electron, because electron is a subatomic particle, and the Schrodinger's equation has to be inherently used. All this becomes highly mathematical, and in day to day understanding of your devices, if you understand an LED, for example, how an LED works, or how a MOSFET works that makes your transistors, processors, your Intel, everything. If you want to understand all these day to day devices, then solving the Schrodinger's equation or doing a quantum mechanical analysis every time becomes tedious. It will need supercomputer and all these things. It's a lot of mathematical work. But if you can apply classical physics equation like F equal to ma, things like that, very simple equation, then life becomes easier. So, all classical physics equation can be applied to electron, although ideally you should not be able to apply classical. If you try to understand, classical physics equations should not be applied or cannot be applied to subatomic particles like electrons. They can only apply to bigger particles, macroscopic things like a table, a chair, a Costco ball, a football, and all these things you can apply classical. But if you talk about electrons and all these things, subatomic particle, you should not be able to apply classical physics equation. But because you have taken all the quantum mechanical information in d square E by dk square, we can use classical physics equations to electrons in semiconductor crystal, okay, as long as we use effective mass. So, as long as you use effective mass, okay, as long as you use effective mass, you are going to include the quantum mechanical information inside this particular term, which you do not have to solve or do anything, it will be given, okay. So, as long as you use a effective mass, we are free to use classical physics equation on a subatomic particle like electron and still get fairly accurate results or mathematical understanding of the devices. So, this is one beauty of the Ek diagram, that it condenses all the information into this, and then it allows you to use the very simple high school classical physics equation even on particles like electrons. That is the beauty of the equation, okay. Now, these things you do not have to solve. Typically, this effective mass will be given. For example, the effective mass of electron inside semiconductor crystal, for example, gallium nitride is a semiconductor, and effective mass of electron inside the crystal will be 0.2 times the free electron mass. So, it is actually lower in a way. It can be higher also, but for example, in a material like gallium arsenide, it is another semiconductor that is used to make your very high speed transistors. Your effective mass of electron will be 0.06 times free electron mass. So, this particular information basically captures all the quantum mechanical picture. You do not have to bother about it. So, as long as you use m star equal to 0.20 m naught for gallium nitride, for example, different materials have different effective masses, by the way, okay. Different materials have different effective masses of electron, okay. That is one thing. So, as long as you use these effective masses, you can freely use classical equation to understand the electron transport. That is the beauty, okay. Of course, I told you different materials have different electron effective masses, and another thing is, if you take a crystal, for example, if I take this hexagonal crystal of gallium nitride, right, I keep telling you this, if I keep taking this crystal, then it is possible that whether you are looking at this direction or whether you are looking at this direction, your effective mass may change, which is what to say, the effective mass can be anisotropic. You have a crystal, right, you have a semiconductor crystal, but whether you are looking towards the top or looking towards the side, your effective mass might be different in different material. It is called anisotropic effective mass. It is not universal, some materials may not have that property, some materials may have that property. So, what I am saying is, if you take a wafer, a semiconductor wafer like that, right, whether you are looking at a transport this way, like there is a metal pad here, there is a metal pad here, you are looking at transport this way, or you have a metal pad here and a metal on the back side. So, the electron is moving in this direction. Depending on whether it is lateral or vertical, your effective mass might be different. It is called anisotropic effective mass. We will not consider it here, but it is very much possible that effective mass might be anisotropic. For example, in silicon you have different direction and you can have different effective masses. Okay. I was telling you here number one thing, right. What is the number two thing? The number two thing is that for effective mass, okay, the number two thing for the effect, these are very important concepts, that is why I am spending time to understand that. Number two thing, I told you that it's inversely proportional to curvature. So, suppose I have a material whose EK diagram, okay, whose EK diagram say looks like this, and then I have another material, okay, EK diagram. Suppose this is EK, suppose this is one material semiconductor X and this is another semiconductor Y. Okay. Now, this EK diagram here, it looks like this. It is also a parabola sort of thing, but it looks like that. Now, you can see that this has a higher curvature, doesn't it look like? It has a higher curvature because it is curving sharply here, and this has a lower curvature. This has a lower curvature, right. I told you the effective mass of electron m star is inversely proportional to the curvature, right, is inversely proportional to curvature. Okay. So, if this has a higher curvature, then this means this material will have a what? Is a higher curvature, no? It will have a lower effective mass. Okay. What I am trying to say is that, of course, your EK diagram can keep changing, although it will look almost like parabola, but it is very possible that, it is very possible that one material has an EK diagram which looks like this, very high curvature, and another EK diagram has a material which EK diagram looks like this, sorry. Okay. So, the curvature here is high, very high curvature, the curvature here is very low. So, if you have a higher curvature, then effective mass will be, higher curvature will have low effective mass and lower curvature will have higher effective mass. Now, you may ask, so how does this effective mass being high or low matter? It matters tremendously in your devices. If your effective mass is low, then there is something called mobility. I will come to that maybe few classes later. There is something called mobility of electron. Okay. There is something called mobility of electron. If your effective mass is low, then mobility of electron is high. If you have a higher electron mobility, then you get higher current. You get higher current in a device, you get superior transport, you can carry very high current densities, very useful for high power, high speed electronics, for example. So, you want a low effective mass material, you do not want a material with a higher effective mass. So, this EK diagram actually tells you so many things, right. See, it has a lower curvature, right, because it has a lower curvature, it has a high effective mass, right, and that is why this material will be basically slow. It will also be carrying lower current, it is not a good material, right. So, this kind of things can be inferred for making devices from the EK diagram. So, that is a very important concept we have learned. Okay. So, what did we learn so far? That electrons move in a periodic crystal, and because they move in a periodic crystal, their parabola is distorted, and because their parabola is distorted, you have this EK diagram that basically fragments into different distorted forms. So, you have something like that, then like that, right. Higher order bands keep coming. I said that first look at the first zone here, it is called the first Brillouin zone between minus pi by a to pi by a, and most of the physics and most of the electron transport will consider only this band. So, we call this the first Brillouin zone, okay, BZ Brillouin zone. We first consider the first Brillouin zone and we confine ourselves to the discussions here. Okay. There are many things associated with a periodic potential, how to solve the Schrodinger's equation, and the periodicity of the potential also helps solving the Schrodinger's equation by putting some boundary conditions. There are things like block oscillation, block equation, like this, because of this periodicity that comes there, you can put some boundary conditions there. We have not covered those. Those are not very essential from this course point of view. We have this course is actually, it does not need a prerequisite, so we cannot go into much details here, but the first zone basically will be enough. Okay, the first zone will be enough to understand all the physics, all the devices that we will talk about in the course. So, I told you the curvature of this zone EK diagram Very importantly, it basically captures the effective mass of the electron, and it's not exactly a parabola, it's a slightly distorted parabola, but close to 0 it's still a parabola, and the effective mass can be derived from the second derivative. So, that we know, and the effective mass has a huge role to play in how you devise the devices, design the devices. So, that is very important, and I told you the effective mass can be different in different directions in the same crystal in some materials, right. Effective mass values typically say lower than the free electron mass in space, it can also be higher in certain materials. So, it is all depend on the crystal structure in a way, right. So, this is what essentially about the EK diagram was, and now going ahead we shall introduce a very fundamental concept actually. The very fundamental, see, we are talking about electrons, right, we are talking about electrons. Remember, this is EK diagram, but if I talk a realistic diagram, I told you in the last lecture, there is a conduction band here which is nearly empty if you recall, and then there is a valence band here. I told you how bands are formed. If you recall, you remember how bands are formed. Do you remember how bands are formed? These bands are formed when discrete energy levels of atoms, they split into continuum of many discrete levels when you bring the atoms close together, and eventually when you have a large number of atoms coming close together to each other to form a crystal, then these discrete energy levels will form into a band. Okay, it looks like a band, and this band is completely filled with electrons. This is mostly empty of electrons, but there is a gap here between them two. It is called the energy band gap. We denote it with E subscript G, right, and then this is called energy band gap. It is a fundamental material property of every semiconductor. Every semiconductor has a band gap. This band gap, this gap between these two can have values that can range from 0.1 eV or even lower to even up to 6 eV. There is a lot of range of band gaps available, but typically semiconductors like silicon have a range of say has a value of 1.1 eV, right. 1.1 electron volt is the energy separation between the fully filled conduction band, valence band, and the empty conduction band. You can actually excite it, this is filled with electrons, you can actually excite electrons from here to here, here to here you can put, and these electrons are now free to move because this band is empty. So, energy states are empty. When their energy states are empty, electrons can easily move. If it is packed here, then electrons cannot move, right. If it is packed with electrons, then how can they move? They cannot, but here this is empty. So, if you can excite electrons from here, then the electrons can move, and that is how they can carry current, and this electron movement in the conduction band was what actually we had described in the EK diagram, right. The EK diagram, and not a very good drawing person, but this is EK diagram, it's and this EK diagram, this particular energy that I had drawn, this band, this band actually is the conduction band, okay, is actually the conduction band, which is this. This is in real space, the x axis is distance in centimeter, okay. This is in reciprocal space, x axis is k momentum, which is centimeter inverse, you can say, right. This is centimeter, okay, a meter. So, this is real space, this is conduction band, right, and this is actually what I had drawn here. This EK diagram actually represents the conduction band in the k space, which in real space is a straight line here, of course, right. So, that is actually how we relate it. This energy band gap, by the way, changes with temperature, it is very strongly dependent on temperature, okay. If you increase the temperature, decrease the temperature, this will shrink or become large and so on. Now, the most important thing that I will introduce very quickly, and as we go into the next lecture now, we will stop and we will go into the next lecture, but the next lecture we will discuss about what happens when electron goes from the conduction band to the valence band, which is fully filled, goes from the valence band to the conduction band where it can carry current. When it goes, what does it leave behind? It leaves behind a hole. Electron has gone to conduction band, so it leaves behind a hole. So, that concept we will introduce in the next lecture after this, and from there we will take forward to the statistics and how electrons and holes are distributed in the bands, and then we are ready to understand devices. Okay. So, here we will end the class.